This is Algebra 1B Part 1, Unit 4, Lesson 9. We're talking about something called compound inequalities. We've already talked about inequalities. When we talk about numbers that are less, we go left. When we talk about numbers that are greater, we go right. When we talk about equality, we draw a circle and fill in the dot. When we talk about less than without an equal or greater than without an equal, we draw a circle and leave the dot open. Okay, so we're going to combine those, and we're going to use the combinations or and and. Let's put it this way here. You can have vanilla or you can have chocolate. That means you can choose either one, right? You can have vanilla and chocolate. Means that you get both simultaneously. So when we graph an or, we include both regions. When we graph an and, we only graph the overlapping regions. Okay, so let's do a few examples here. X is less than -2 or x is greater than 1. Less than -2, so I'm going to put a circle above the -2 and shade to the left. Or x is greater than 1, and x is less than -2, not 1 there. X is less than -2. Or x is greater than 1. Okay, so we would take both combined with an or. We would say x such that x is greater than or less than -2, or x is greater than 1. And I realized something. I meant to do an equal to on one of these, so I'm going to put equals to. Okay. And so that's the graph of the or. Notice that it's the union of the two sets, not the intersection of the two sets. Okay. X is greater than or equal to -2, greater than or equal to, and less than or equal to, fill in the dot. Greater than or equal to, now it's going to go to the right. Or x is less than 1. X is less than 1. Now here, any part that gets covered by either graph gets covered by the whole thing. And so we would say x is all real numbers. Or the solution set is all real numbers. All real numbers. Because the actual overlapping part of the graph is everywhere. Okay? As opposed to x is greater than or equal to -2. And x is less than 1. The overlapping part is from including -2 to +1 exclusive. And so we say x such that, and this is read as x is between -2 inclusive and 1 exclusive. Okay. Okay, and then this one, x is less than or equal to -2. And x is greater than 1. We're looking for the overlapping part. There is no overlapping part, so the null set or empty set is the solution. Or empty set. Empty set. Okay? And you can do this a number of ways. We can see this in context a number of ways here. Let's go ahead and do a problem like you'll be given in the problem set. Let's say we have the compound inequality. X is, or 3x is less than -27, or x is greater than, or x plus 10 is greater than 11. So we would solve both inequalities, remembering that anything that happens to the left happens to the right. Divide by 3. We end up getting x is less than -9, or add 10 to both sides, or subtract 10 from both sides. X is greater than 1. So on a number line, here's -9, -8, 7, 6, 5, 4, 3, 2, 1, 0, and 1. It would be less than -9 or greater than 1. So it's the combination of both sets. So we would say the solution set is x such that x is less than -9 or x is greater than 1. Okay, that's for an or, a union solution. What if we have a intersecting solution? What if we say x is between -20 and inclusive? Let's say it's 3x plus 7. And let's say it's 22. Yeah. Had to come up with something that would come out to be a decent number here. In this case, we treat this like a three-way inequality. Anything we do to one side, we do to all of them. Subtract 7 from all three. We get -27. Now we'll see if I set up the arithmetic right. 3x and -7 is 15. Yeah, there we go. That's what I was trying to do, was make sure that we had no fractions. And then divide all three sides by 3. And we would say -9 is less than or equal to x is less than 5. Okay, if we think of -9 on the number line, 8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. X is greater than -9 or equal to, and it is less than 5. That's one set, so one region. So we'd say x such that x is between -9 and 5. And any part of the graph within the shaded part is a solution of the set, or a solution of the original inequality, compound inequality.